So that's if you have relevance. And of course, in practice, nobody's going to give you examples of relevant documents when you have to rank, right? After you've done the ranking and the user has looked at things, the user may say, okay, I like this one, I don't like that one. But that's after. How do you rank before? How do you rank the documents by probability of relevance before you have any examples? And the answer is not very pleasant, so there is no way you can estimate PW and QW, but the guys who came up with the model weaseled their way around it by introducing a bunch of other assumptions which are relatively innocuous on the surface and allow them to compute something at the end of the day. Right, so let's look at the assumptions that they made. The first assumption, they said that if the word is not in the query, it's going to have an equal probability in the relevant class and in the non-relevant class. So PW and QW are going to be the same thing, right? PW equal to QW if the word is not in the query. So what does it mean? It means that we're going to take this expression, and if the words are not in the query, then PW is going to be the same as QW, so they will cancel out. And 1 minus PW and 1 minus QW are going to cancel out as well. So what this does, what this assumption does, is it turns it into a product only over the overlap between the document and the query. And at this point, it becomes quasi-linear, right? Because I can take the log of that thing, and then I just have sum of the logs of these guys, right? And the sum goes over the intersection, so it's linear, and I can do trim at a time, right at this point. Okay, next assumption. I still have to estimate the PWs and QWs for words that are in the query. So the assumption that they make is that if you have a query word, a word is in the query, it's going to occur in about half the relevant documents. So PW is going to be 0.5. Now, why are they doing that? Is that reasonable? No, but in the absence of any relevant examples, that's probably as good as any other estimate that you're going to come up with. Because remember, nobody's giving you examples of relevant documents at this point. So they're just saying that PW is going to be 0.5, and that means that half the relevant documents will contain a query word on average. Okay, great. So when you do that, PW and 1 minus PW are going to cancel out, and what you're going to be left with is this formula. It's the product over the intersection between the document and the query. You have 1 minus QW over QW. Now, we still have to estimate these guys. And here, the estimation trick is a little bit, just a tiny bit cleverer than before. They're saying, think about what you want to estimate. You're trying to estimate QW. What is QW? QW is you take a random, non-relevant document. What is the probability that it's going to contain the word W? Now, nobody's giving us examples of non-relevant documents, so we can't count it directly. But what do we know about the class balance in information retrieval?
Very little relevant documents.
I'm sorry?
Very little relevant documents.
Yeah, so your corpus is almost entirely non-relevant stuff, right? The relevant documents are a tiny, tiny fraction of it. So what you can do is you can take your entire corpus, your entire collection, count how many documents contain a word, and that's going to be a pretty damn good estimate for the probability of the word in the non-relevant set. Because the collection as a whole is a very good estimate of the non-relevant set, right? So 99.99999% of the documents are non-relevant. So taking the whole thing as an approximation for the non-relevant set is a very good action, right? So you can do that, and if you do that, that is the formula that you get. You get a product over words in the intersection between the document and the query. 1 minus QW over QW, you can work it out, it becomes that. So N is the total number of documents in the collection. NW is the document frequency. It's how many of those documents contain a word. And here you get the document frequency again. Right? And if you look at this really hard, and I guess what's going to help it even more is take this whole expression and take a log of it. Right? So what happens if I take a logarithm? Right? Logarithm of a product is the sum of the logs. So what I'm going to have left is the summation over the words in the intersection of the documents in the query times log of n minus nw. I'm going to forget about the constants for a second. Divided by nw. And that is something that you have seen before. Right there. Okay? This C is the number of documents in the collection, and this N is the number of documents in the collection. DF is the number of documents that contain the word W. That is the number of documents that contain the word W. I'm subtracting NW here, does it matter? No. I mean, this is tiny, this is big. And besides, they're monotonic. You can plot this as a function of that. Straight line. Okay? So, that part is the IDF component. And you have the summation that looks pretty much exactly like that summation over there, right? Because this, in fact, only goes over the intersection between the documents and the query. Because otherwise the TFs are 0. Okay? So that is the same as that. And that is actually not a coincidence. Because this part of TF IDF weighting was adopted by the vector space guys when the probabilistic guys came out with this. So it's, it happened a long time ago, but it's sort of a certain very well-known lady, Karen Spark-Jones. She was working with Steve Robertson on the development of the probabilistic model, and they churned it out, and they came to this, and this started working really, really well. At the time, nobody was using IDF, because IDF didn't exist. Nobody knew that that's what you have to do. So they started using this, and then the guys who were doing the vector space model, the cosine, they said, why are they beating us? What is it? Yeah, they talk about all the probabilities, but really, what is it that makes their model tick? So they took it, decomposed it, and said, that part. The part that comes out during the derivation of the probabilistic model, they took it, placed it in their cosine, and things took off, and they got much better results. Right? So it's an example of a component, a formula that was derived formally by the guys working in the probabilistic space, and then adopted by every other retrieval model out there. So every model that you have makes use of IDF, just because it works so well. Right? But remember, that IDF, it didn't come out from blindly walking around the maze, just trying out different formula. It actually was derived. All right, I'm going to stop here, continue in the next lecture.